In this lecture, we'll build the functionality that allows only specific items to be stored in an inventory. This is useful for things like a forge, where you may want to restrict input to only certain crafting resources. Let's go. We jump right into our BPC inventory and start by creating a new variable named allowed item types. This variable defines what types of items are permitted in this inventory. Set the variable type to an array and change the type to soft object reference of PDA item data. This allows us to assign item types without hard referencing them and keeps it flexible for future assets. Move the variable into the category inventory settings and set its replication mode to replicated. We replicate it because every client needs to know what types are allowed. It might also change at runtime, so full network awareness is essential. While we're here, let's organize the rest as well. Move the slot amount variable into the same inventory settings category. Do the same with max transfer item distance, so all core settings are grouped together. Now compile and save, and we're ready to move on. Over here on the right, where we're creating the slots, drag the allowed item types variable into the graph and set it as a set node. Now we add a new custom event and name it setAllovedItems_server. We use this as a setter function so we can define or change the allowed item types at runtime. For example, when spawning a container or updating its settings dynamically. In the details panel, set the replicates property to run on server and mark it as reliable. This ensures the change happens authoritatively and replicates correctly to all clients. Add an input to the event and name it allowed item types. Set the type to an array of PDA item data using a soft object reference. This gives us a flexible way to define allowed items without directly referencing the asset in memory. Quick note: small mistake I made when recording. I forgot the _server suffix in the event name, and the input was originally named just allowed items. Not a big deal, but if you're following the tutorial step by step, feel free to adjust the names so they fit better and stay consistent. Now connect the allowed item types pin from the event to the input pin of the set node to assign the value into the variable. To confirm the function is working, we add a simple print string at the end. What you type into the message is totally up to you. Just something that helps you know the function was triggered. Now select the entire section and wrap it inside a comment block labeled Inventory Settings. Reposition it neatly in the graph so it's clearly structured, and that's it for this part. Now compile and save the blueprint before we move on. Next, we'll create the function that actually checks whether a given item is allowed in this inventory or not. Add a new function and name it as slotItemAllowed. Move it into the transfer category to keep it organized with our item logic. Set the function to pure and mark it as const, so it's read-only and does not affect runtime behavior directly. Add an input named slot and set its type to sInventorySlot. Make sure this is a single variable, not an array, since we want to evaluate one item slot at a time. Add an output named returnValue and set the type to Boolean. This will tell us whether the item in the slot is allowed, based on the rules we define next. Make some spacing between the nodes, so we have space for our logic. Now drag the allowed item types variable into the graph and place it as a get node. From this node, call is empty. This function checks whether our allowed item types array currently has any entries defined. If it's empty, we'll treat the inventory as unrestricted, meaning all item types are allowed. Next, move to the function's input pin and add a break s_inventory_slot node. In the details panel, hide all unnecessary pins and show only the item data asset pin, since that's the only one we need for this check. Then go back to the allowed item types node and call contains item, which is found in the array category. This node allows us to check whether the provided item data asset exists inside the allowed item types list. It returns true if the item is found and false if not. Now connect the item data asset pin from the break node to the second input of the contains item node. This links the item we want to store to the comparison logic. Then connect the return values of both the isEmpty node and the contains item node to an OR operator. Finally, take the result of the OR operator and connect it to the return value pin of the function. What we're doing here is simple but powerful. We check: is the list of allowed item types empty? If yes, all items are allowed by default. If not, we check: Does the item exist in that list? If either of those is true, the item can be stored. Now we need to use the function we just created in two different places within our inventory system. The first place is inside the add_item function. Open it up, and scroll to the very beginning of the function. Here, disconnect the wire between the item to add input and the set node for current item to add. Then connect the item to add as a get node directly to the current item to add set node. The small f above the variable node indicates that it is the input of the function. This avoids a long cross connection from the top of the function and keeps the graph cleaner and easier to follow. Right after the item to add input, add a branch node. Then call the isSlotItemAllowed function and connect it to the branch's condition pin. To do that, use the item to add input as the value for the function call. This allows us to directly check whether the item that's about to be added is even allowed in this inventory. Now, on the false execution pin of the branch, add a return node, and leave the successfully checkbox unchecked. That means the function will exit early and return false if the item type is not permitted, stopping the add process before anything is committed. The second place we need to use our check is inside the add_item_to_index function. Open it up, and again, we'll start right at the beginning of the function. First, create a bit of space to work with. Now disconnect the existing connection between target index and the index pin of the getSlotAtIndex node. Instead of a long line across the graph, pull target index in as a get node and connect it directly to the index pin. This keeps the flow more organized and visually clean. Then, just like before, add a branch node immediately after the function input section. Now call the isSlotItemAllowed function and connect it to the branch's condition pin. Use the item slot to add input as the value for the function call. This checks if the incoming item slot matches the allowed types for this inventory, before we try to place it at a specific index. Then take the false execution pin of the branch and connect it to the existing return node further down in the function. This ensures that if the item is not allowed, the function exits early and nothing is added. What we're doing here is making sure that both entry points, whether items are added regularly or to a specific index, respect the allowed item filter logic. That way, no item type can bypass the rules, no matter how it's inserted. Just short ad. Here is an video shows you a quick preview of what you'll learn in the MSG course. Step by step, you'll build a complete survival game in Unreal Engine 5.5. With everything you need to make it fully playable and multiplayer ready. You'll master motion matching, procedural animations, and build your own inventory, crafting, and building systems. All blueprint only, no C++ required. We also include exclusive assets, clean system design, and a structured, professional workflow that you can use in any future project. Whether you're a beginner or already experienced, this course will guide you through every major gameplay mechanic, clearly explained, fully modular, and multiplayer compatible. Check it out. Links in the description. Now let's head back to the map view and select our large storage box in the scene. We want to define that this specific container should only accept hammers. You can do that directly from the viewport by selecting the actor, then clicking Edit BP Storage Box in the outliner, or by locating it in the content browser. Either way, it takes you straight to the blueprint of this storage actor. Switch to the full blueprint editor to work with the logic and components. Now select the storage inventory component in the components list. Just as a reminder, this storage box inherits from BP Storage Master, where this inventory component was originally assigned. On the right-hand side, in the Details panel, we now see all inventory-related properties under the Inventory Settings category. Here, we could already predefine the allowed item types array. Technically, it would work, but it's not a recommended approach. And why is that? Because if you set array elements here directly in the parent class, these values are stored as default values. That means all storage boxes using this blueprint would share the same restriction. It limits flexibility and prevents you from setting different rules per instance, which is exactly the point of exposing this property. The better approach is to assign the allowed items at runtime, not directly inside the Details panel. This way, we stay flexible and can later pull that information from a data asset, or some other external source that defines inventory rules for specific containers. Let's start by adding a begin play event in our storage box blueprint. Then select the storage inventory component and drag it into the graph as a get node. What we want here is to call the setAlloudItems_server event to define what items this storage should accept. But here's something important to notice. We could technically also just drag in the AllowedItemTypes variable and use a set node to assign values directly. Yes, it would work. But now comes the part that's easy to overlook. What happens when we set the variable directly? Let's switch over to the inventory component and take a look. When we use the set node on the variable instead of calling the event logic is completely skipped. That means everything we planned to do inside that event, like checking for invalid items, removing them, dropping them into the world, or sending an update to the UI, would never happen. This can cause serious issues later, because logic that you think is running just isn't. To prevent that, and to make sure the event is always used, we go back to the variable AllowedItemTypes and set its access to private. That way, it can only be changed through the proper interface. Now let's add a new function inside the inventory component and name it getAllovedItems. We'll use this as a getter, since the variable is now private and can't be accessed directly from outside anymore. Move it to the getter/setter category. Set the function to pure and mark it as const. That just means it doesn't modify any data, it simply returns the current value of the variable. Inside the function, add a return node. Then drag the AllowedItemTypes variable into the graph as a get node, and connect it to the return node. Unreal will automatically generate the correct output pin for us. Now compile and save the component, and head back to the storage box blueprint so we can continue from here. First, let's connect the begin play execution pin to the set node we just placed. But the moment we try to compile, we get an error. That's because the variable AllowedItemTypes is marked as private, so we can't set it directly from here. And honestly, that's exactly what we want. By restricting access, we make sure that this value can only be assigned through our custom event function. That way, our logic stays clean and reliable. Any follow-up actions like checking for invalid items, dropping them, or triggering updates will only happen if we use the correct interface. So let's delete the set node now. Instead, we call the event setAllovedItems event, and you'll notice, we can now only access the event and the getAllovedItems function, which returns the current array. These are the only ways this variable should be handled from outside the component. Reconnect the execution flow so everything lines up again. Now, just to simulate a real setup, we promote the AllowedItemTypes pin of the event called to a local variable. Later, this could easily come from a data asset or another system that defines what each container allows. Let's compile once so we can assign a default value to this variable. And for testing, we'll choose our DA hammer item. This will be the only allowed item for this specific storage box. That's all we need for the logic. Let's hit play, switch the net mode to play as client, and see what happens. If you're enjoying the course so far, feel free to leave a like or even subscribe. It really helps and keeps this project going. Once we're in the game, we already see the print string appear in the top left corner. That tells us the restriction was applied successfully. Now let's press T key to give ourselves some items, and head over to the wooden crate. If we try to move something like the pumpkin or the raw meat into the crate, it doesn't work. The inventory refuses those items. But when we drag the hammer into the crate, it works. The item is accepted and stored correctly. So no matter how we try it, this crate now only allows hammers. If we walk over to the crate next to it, which has no restriction, we can still move any item back and forth without a problem. What's still missing at this point is visual feedback. And that's exactly what we'll take care of in the next lecture. We'll highlight inventory slots in red when an item isn't allowed, so players know immediately what works and what doesn't. Thanks for watching. I hope you enjoyed this episode. See you in the next one.